If we're in a dense ocean of matter, then fission and fusion should occur. And this is because with fission, you've got the matter boiling off, like if you have a lump of something, and if the density around that matter is not strong enough to keep it together, pieces of that matter will fly off into space, and it will fission away because of the lack of pressure around it. And this dictated by the general pressure of the matter universe pushing in on it as to whether or not it's going to be radioactive or not, that substance. For example, every atom that's larger than bismuth is radioactive. That's every element. There are other elements as well that can be radioactive when they're smaller, if they're of a particular isotope. Again, it has to do with what the matter can get around it to stay together. For example, certain isotopes, much smaller than bismuth, can also be radioactive if they're too large for what's around them, to help hold them together. So it really depends if a piece of matter is going to survive in this matter universe as a whole without flying apart, without fissioning away. It has to be able to get enough stuff around it to help hold it together. Now, fusion is the opposite of that, but also has directly to do with the matter universe, that is the ocean of matter that we're all in. According to the density of the matter universe, if a substance is too small, it will fuse to other pieces around it because the other pieces are actually pushing these other pieces together. So if it's got too much stuff around it, and it can cut through what's already around it, the smaller stuff that's already around it, then it will fuse together. Now this happens in the sun. Of course, fusion only happens when there's enough pressure, or when it can cut through all the little pieces that are already around it. And this is why cold fusion doesn't work. For example, if you have two balls, say of hydrogen, say these two balls are hydrogen, and you've got one proton, and you've got the stuff that's around the proton, and stuff that's around this proton as well. Here, wait a minute. There, stuff that's around this proton and stuff that's around this proton. And in order to cut through the stuff, you're going to need heat, and this heat's, joggling it, bumping it, and once it has enough acceleration to actually get close enough, then it will fuse. Now, when that fusion happens, what's going to happen is, when these come close enough, just like, remember how I explained gravity, how it's just matter covering other matter's surfaces? This is the same thing. It's again a gravity that once it gets past its own, stuff around this ball and the stuff around this ball, it will, once it contacts, it will fuse. Once it does that, it's this extra stuff, the fine stuff that was around these pieces, fling out. And the finer stuff that flings out is considered to be energy currently. But it's not energy, it's just fine matter. So we see that energy doesn't actually exist like solely by itself or anything. It's just the push of matter is all energy ever really is. There's no such thing as energy that just magically exists somehow separate from the matter. No. Energy is just push of the matter. That's also another important thing to understand. And with fusion, you can see the gravity of it, it's stuck together. And that's fusion. Two hydrogen atoms, heat or pressure and heat and pressure can cause them to fuse together, thus violently throwing the finer stuff out. Now, of course, they're still surrounded by fine stuff, but not as much, because there's not as much space around them now. to allow for that other stuff to fit. And that's why fusion provides finer matter flinging out away from this group, because it flung out because there was no space around the two pieces of matter, that is the two protons. So that's what fusion is, and that's what's happening in the sun. You can see now why cold fusion is impossible, because what's around, before they're fused, what's around this one and what's around this one act as a buffer and shield each other from getting close to each other. You know, it's the same reason why electrons will not, you know, if these were two electrons instead of two protons, the same thing happens. You push them together and they spring away. Why? Because there's stuff around this one and there's stuff around this one. It springs them away. And that's why the electrons space each other out. Now, with fusion though, you know, getting back to fusion, the once they're stuck together like that, it's very, very strong, and it's hard to disconnect them. Why? Because they're filling holes very efficiently according to what's around them in the matter universe, the density of the matter universe, and that's what fusion is. And of course, fission being the opposite of that. So cold fusion is an impossibility, because you have to cut through the cloud of stuff, the buffer of stuff that's around these particles, in order for fusion at all to happen. Now, you could consider it cold if you could blow something between them and cut through the cloud so that they can be drawn together and fused together. But you know, you still have to end up having to push them together or something. Once they get close enough, you know, the holes suck them right in and they stick together. So that would be fusion. Now, the fusion happens because the density of the ocean of matter is great enough to help push them together. Now, fission is, of course, the opposite, when the density of the matter universe can't hold it together and things fly apart. They're literally sucked apart by the finer matter coming in around them and drawing them away. So when the finer matter, imagine two balls again. When the finer matter, you know, they're like say there's a whole lot of balls fused together, and the finer matter, they're just a little joggling, and the fine matter rushes around one of the balls, and as it rushes around the ball, it takes that ball away. So say you had a whole lot of balls. Whole lot of balls stuck together, more than this, of course. Say this is uranium or plutonium or something like that, and of course it requires a lot more protons than this, and the finer matter would come in and say this ball's about to fly away, because the finer matter will rush around this ball and just draw it right away. And why is it drawing it right away? Because it's rushing around it, and therefore becoming its cloud again and drawing it away. All because the density of the ocean, that's why I used to call it oceanos, the density of the matter universe, the ocean that we're all in, is not dense enough to hold it together, and so any little joggling of that uranium or plutonium draws it away, causes that evaporation to happen, and that's why things fission away. It can be slow fission, it can be fast fission. It just draws it right away, really quickly. Now, of course, this drawing away and what's stable above elements above bismuth, you know, they're not stable because the ocean of matter around them isn't dense enough. But if you increase that density, and in some places in outer space, indeed, that density is greater than what we have here, which is why the uranium and the plutonium formed in the first place. So, the fact that we have uranium and plutonium means that there were denser places in outer space that these things formed. So, if you have radioactive, say, carbon dating, or any other form of radioactive dating, it's going to be susceptible to the ocean of matter that's around it. Because if that ocean of matter is more dense, then the radiation, the fission will be slower, and it will seem like to the scientists that more time has passed than it actually has. If you have the opposite of that, if you have a less dense amount of stuff around the radioactive element, then that stuff will fission, less dense, then it will fission away faster. And if it's fissioning away faster, then the scientists who are relying on, for example, carbon dating, will say, oh, it must be that it's things are happening faster. But this is all subject to the change of the density of the oceanos. So, is radioactive carbon dating or any other form of radioactive dating reliable? Well, no, because it's subject to what's around it. Evaporation, for example, of water happens faster at higher altitudes because there's less stuff around the water to help keep it together. It'll evaporate faster. This is the same way with all radioactive dating, with all radiation. And this is also verified. This is not like a, theory or anything. Of course, nothing I say is a theory, but this has also been recently proven. They've recently found out within the last few years that this is indeed true, that even with the Earth, even with the small pocket of space that we know about for now, with where they say that there's the sun and the Earth goes around the sun. Well, when you have the Earth going around the sun and a certain time of the season when the Earth is in a particular part around the sun, the oceanos is less dense, and another part of the orbit around the Earth, the oceanos is more dense. I should say, not oceanos, but ocean of matter. Anyway, the ocean of matter is less dense or more dense here, less dense there perhaps, and what happens is they found out that the radiation actually does change. And I kind of thought that would make the news, because people are like, wow, scientists have relied on carbon dating and other forms of radiation, even atomic clocks, to keep very, very good time. But the fact that it changes over the course of a year, just a single year, according to where the Earth is around the sun, how could we possibly know many years? How could we possibly know, for example, 1,000,000 years, when even a single year changes the radioactive dating of trying to date things with radiation? And the fact that things radiate faster, just according to where you are in the orbit around the sun, they've also had to adjust things like the radiation treatments for cancer patients, according to how fast the radiation is emanating from the elements that they use to treat these cancer patients. And so that's another reason why they've just recently started to adjust this. So even radiation and fusion and nuclear bombs, which would be fast fusion, even these things show that the ocean of matter exists, because these things are directly responsible for the pressure of the matter universe is directly responsible for fission and fusion. And without the matter universe, nothing would hold together. Everything would explode out into finer and finer pieces. The fact that we have pressure here means that there's pressure way, way, way out there. And that pressure is endless, which means the universe of matter is endless. And it has to be, because we know it is, because we have pressure here. And if we didn't have pressure here, then that would prove that there's not pressure out there keeping us together. So the fact that we can even stay together means that the universe is, in fact, endless. Besides radiation and fusion, there are more things that show that the ocean of matter exists, and we'll explore more things later. Things like electric attraction, electric repulsion, and what will be discussed next, and eventually magnetism, both magnetic attraction and magnetic repulsion, which would be diamagnetism, and the two different kinds of diamagnetism that I've discovered.